Welcome to another episode of Yo at Home. Now we're going to be talking about how igneous rocks and plate tectonics all go together. So to start with plate tectonics, we remember gravity is working on the planet, so more dense material is pulled down. The most dense of all is going to be your radioactive material, way deep down, and that's going to be heating the Earth for all these billions of years. So a lot of the heat from the Earth is just from that radioactive decay of that material giving off that heat. So it keeps the Earth quite hot, and you will have convection cells. This is the top of a convection cell. Convection is when less dense heated fluid rises because more dense fluid is pulled down. So this is heated material coming up, rising, spreading apart. All right. Well, as it spreads apart, it rips open the crust and intrudes some of this material from deep down in the asthenosphere. Well, what would the asthenosphere be made of? Mafic material. Very mafic material because it's dense, it sinks lower, even ultra-mafic material. So very dark, dense rock coming up here. Well, right here meets the ocean. What kind of rock is that going to be? It's going to cool very quickly. So, yeah, that's going to be your basalts. Right? Basalt, gabbro underneath that. So the mafic rock is forming the seafloor. The seafloor is brand new here, and as it spreads apart, new rock is always being intruded here. So this rock is getting older and older and older as it goes across the seafloor. Made of mafic rock. And you can see anytime you have rock coming up from the mantle, that rock is going to be mafic. Why? Because the mantle is mafic. Easy enough. So the rock spreads across here. It gets older, and as it gets older, it also, of course, gets colder. Okay, so as it gets older and colder, eventually, why does that matter so much? Well, older, colder goes with one other thing: more dense. When it was quite young, it's still hot, less dense. As it gets colder, it gets more dense. Eventually, it gets so dense that it is going to sink, and it will sink, and it'll go down with the sinking of this convection cell. So this is being pulled down. Friction with the convection cell is doing this whole thing, and friction with it is also pulling this down. So as it pulls down, what's going to happen to this basaltic sea floor? Well, it's not only basaltic, it has seawater in it. It has limestone on top of it from all the dead sea creatures that have been falling on it for the 200+ million years it's been going across the ocean floor. So as it sinks, well, a special thing happens. And this is really one of the things that makes Earth unique, as far as we know, or at least gives us continents and keeps the Earth a really interesting place. What parts of it, as it melts, what parts of it are going to rise to the surface? Well, what parts would rise in a room? How would you get a balloon of something to rise up in the air of the balloon? If it's less dense. So that's all that's going on, less dense. In a room, it would be helium. In rock, it would be felsic material. Felsic material is less dense and rises exactly the same idea as a helium balloon rising in the Earth. So what we would call these are felsic plumes rising up. And these can be huge. These can be 100 miles across or on the order of that. These are very large objects, and they rise obviously very slowly. Many of them will implant right in the crust. When they implant, they will cool slowly. And what forms will they take? That will be granite. Now, the granite is extremely hard rock, very resistant to erosion, and it means the continents aren't going to fall apart so easily. But one of the other important parts about it is low density. Right? Granite is low density. So this low density granite then, this low density granite will remain on the surface, and that's what gives us continents. Some of these plumes will rise up and they will connect to volcanoes. And if they connect to the volcanoes will erupt, and you'll get, all your eruptive things like obsidian or pumice. But your felsic eruptive things, obsidian and pumice, that stuff which cools a little bit faster here would be rhyolite. Again, rhyolite is very uncommon as rock goes, because you're not going to tend to get the rhyolite just staying there long enough to cool very much. What will typically happen is that the granites, the big plumes, will stop as soon as they get here, and they will remain and cool over a long period of time, hundreds of thousands to millions of years, and form large crystals and granites. So it is right here. And what do we call this zone? We have a very special name for this zone. This is a subduction zone. A subduction zone means that you have active plate tectonics on the surface of a planet. Right here we would have a trench, a deep sea trench. The deepest you could get in the ocean would be at one of these trenches, and it's where one plate is subducting underneath another. What is the classic indication that on a planet you have subduction going, which means you have active plate tectonics? Granite. If you have granite on a planet, the only way you can make granite is through this very complex process of working the different rock. A basaltic plate sliding under with seawater, and the new combination of elements makes these felsic plumes, which are made of your felsic material, your granites, and they will in place form continents. Continents cannot subduct. It's like trying to subduct styrofoam in water. It's not going to happen. The density here is so low that these things just cannot get pushed deep down into the mantle. What gets pushed down is always the basaltic plate, which means you're constantly making more granite. So over time, the Earth's continents will continuously get larger and larger. So when you pick up a piece of granite, you're picking up a very special rock that is responsible for making the continents the way they are. And that is how igneous rocks relate to plate tectonics, to how the Earth works as a whole system. New rock is formed here, moves across the seafloor here. It gets older, colder, and more dense. Typically about 220 million years is about as old as an ocean floor gets before it's so old and cold that it begins to subduct. So at that point, your basalt is going to get melted. Most of that will get melted and turned into mantle stuff again, and it'll eventually come back up to the surface on a mid-ocean ridge. But the important part is the little bit of that comes off as your granitic material. And that's going to rise, and that's going to stay there forever. So all subduction zones have these volcanoes coming up. If it happens in the middle of an ocean, you'll have a whole island arc system with a bunch of volcanoes. Think of Japan, the Philippines, and places like that, where all these volcanoes are coming up, and they constantly are making an island bigger and bigger, as is the case with those places. If it happens right on the edge of a continent, well, those volcanic mountains will be right on the edge of a continent, because the ocean floor will subduct. Think of the Andes Mountains in South America. Those mountains are coming up. Think of the mountains like Mount St. Helens in the United States, in the Sierra Nevada range in Washington State. Those mountains are also coming up from a subduction zone. Very violent volcanoes because it's very gassy, and the stuff does not let the gas escape very easily. With all the silica, it makes the magma very thick. And so that is how you do that. Igneous rocks tell you all about your plate tectonics. Thanks.